Hello and welcome to chapter 3.2, which is about different solids and their properties. So these are the solids that we're going to discuss. We got ionic solids, metallic solids, covalent networks, and molecular covalent solids. And the properties that we're going to discuss is how hard they are, their melting and boiling points, electrical conductivity, can they dissolve in water or not. There are other things in there, other properties in there, but they're specific of a specific solid, so we're going to discuss them as we go through this. First of all, ionic solids. So we discussed ionic bond in Unit 2. A ionic bond forms if you've got a metal and a non-metal, and the difference in the electronegativity between them is bigger than 1.8. Some books you might find another number. And then what happens is this metal and this non-metal become ions, and these ions arrange themselves in a lattice like this in a crystalline structure. Here is it in 3D, where each plus is surrounded by minuses and each minus surrounded by pluses. It creates a very stable Coulombic structure that is very rigid. And because there are so many actual connections, Coulombic bonds between them, it's very hard to break this. So these are hard. They have very high melting and boiling points because remember, especially to boil something, you need to make particles move. So here you will have to break all the bonds to make the particles here move. So you'll have to break all the Coulomb attractions, which would be really difficult. So it has a very high melting and boiling point. However, ionic solids are brittle. What does that mean? Well, see, if you just pull them a bit out of this rigid structure, what you will have is instead of Coulomb attraction, you will have Coulomb repulsion now because look at this minus is next to a minus, plus is next to a plus. So if you've seen a big piece of salt, it's really hard, it's difficult to even scratch it. But if you apply enough pressure, it will snap. And this is the reason. Also, a few more things I want you to pay attention to here. So, 99% of the time, when you give an example of an ionic solid, it's going to look exactly like this picture. Why? Well, all the ionic solids which are one to one, such as NaCl, 1A, Na to 1Cl, KF, MgO, they will always have this structure. Well, each plus is surrounded by six minuses, and each minus surrounded by six pluses. If it's not one to one, such as MgCl2, MgF2, for example, then that's going to look different. But it's not really shown in the AP curriculum, so you don't have to worry about that. Also, how hard it is to break a lattice, and especially how high the melting and boiling points are, depends on how strong the Coulomb attractions are here. So the strength of the Coulomb attractions depends on the effective charge of the ion. And in AP curriculum, in all the questions, and actually in chemistry, the bigger charge will always win. What does that mean? So in MgO, you got Mg2 plus and O2 minus, and that's MgO is going to have a way higher melting and boiling points compared to NaCl, because NaCl is plus one plus minus one, and MgO is plus two minus two. Why? Well, essentially, you should say that MgO has ions with higher effective charge. Why? Because the size is almost the same, and we're dealing here mostly with things from group 1, 2, and 6 and 7, and most of the time you'll have very similar size, but you have much higher charge. It's double the charge, 2 plus, and here you got 2 minus, right? Actually, 2 minus. You have 2 plus and 2 minus, and on the other side you have 1 plus and minus, which is much lower. Uh, okay, metallic solids. So these are easily recognized because when they give you just the metal, they say, okay, Fe, what's the bond there? As long as it's one and it's a transition metal, that means it's a metallic solid, right? So what is special about transition metals, as we discussed before, is that they have d orbitals, and d orbitals are much bigger than s and p orbitals, which means basically that uh, there will be multiple overlaps. So each of these ions will overlap with multiple ions around it. So let's say I have iron Fe and iron likes to release two electrons. So you got Fe2 plus, right? So you have ions in there, each one with d orbitals overlapping with neighboring hundreds of other ions. And then that next one overlapping with the next one. So this creates a huge d overlap. It creates a network of overlap. And all the electrons that are released by all these atoms to become ions, all the electrons can now move between them. So essentially, it's like each ion being connected with every other ion. So you can see this is even stronger than ionic bond, because the ionic bond you have mostly one bonded with six, right? Here you have one bonded with everything. So delocalized electrons and overlapping the orbitals enable this structure, which is very hard. I mean, we know that from everyday life, right? It has extremely high melting and boiling points. Uh, it can be malleable and ductile. Malleable means basically you can beat it into different shapes. So basically, you can slide sometimes layers over each other, right? Uh, Depends on what kind of metal we're talking about. And ductile means can be pulled into wire. So again, if you apply pressure, uh, try to stretch it out. Basically, the bonds will still hold, of course, fewer of them, but it will not break. So this is very very difficult to break, very very difficult to melt, very very difficult to boil. I mean, I don't know if we can boil most of them on planet Earth. Anyways, uh, this metals conduct electricity. They're basically the only one of the solids, with the exception of some giant molecular structures, that can conduct electricity in solid state. Why? Because I mean these electrons can move around, right? So if electrons can move around, that means electricity can be conducted. Also, this cannot be dissolved in water. It might seem counterintuitive to you because there are pluses here, so water should be able to latch on the pluses. However, the electrons are moving so fast that they're effectively just spread out everywhere equally. So that means that there's nothing for water to latch onto, so it cannot conduct electricity. Also, what are alloys here? Uh, you have here two examples of two different types of alloys. They don't really insist on this way of separation of types, but an AP. But here you go anyway. So substitutional type of alloy is when you're substituting one metal with another, but there's the similar size. So the green one is just one. Just imagine any metal, and then you just added another metal which is of similar size. So basically, an alloy is like a mixture of two types of metals. For example, you have, we talk about white gold and yellow gold. So yellow gold has some copper in it. So basically, just some of the atoms, some of the ions of gold are just substituted by an ion of copper, and that's why it has that reddish color. And this is, for example, this is what steel is. Steel is this type of alloy. So basically, the green ones in the example of steel would be iron atoms, and then carbon atoms. The orange ones would be carbon atoms which are added in between. What does this do? Well, basically, it makes you unable to slide these layers, such as here. So by adding carbon, which is much smaller than iron and can fit in between the ions of iron, you're basically making an alloy called steel, which is much harder than iron, much harder to break because there's no sliding, but also much less malleable. So you can't really make it into the shape you want. So I mean, you can add other things to steel, is adding chromium or zinc to improve different types of properties. But I mean, this is just an example of just like plain steel. Covalent networks in molecular solids. Okay, this is a bit of a more complicated story. So, first of all, molecular solids are just plain covalent compounds. Let's say this is H2, right? So you've got two types of bonds in here. You've got intramolecular and intermolecular, right? That's not the case with metallic and ionic, right? So let's say this is H2 There's another H2, there's another H2. So inside of the molecule, there's a covalent bond between two H's, right? But in between the molecules, there is just a weak London dispersion in this case, in the case of H2, right? Now, why is this important? Because of melting and boiling and hardness in general. So basically, I told you to melt and especially to boil something. To boil something, you need to completely make particles able to move. So in case of this, I have to break everything in order to boil this, right? But in case of this, I don't need to. I just need to break intermolecular bonds. And as we said, intermolecular bonds are much weaker than metallic, ionic, covalent. So it's very easy to break them. So usually molecular solids have very low melting boiling points and very weak. Usually, I mean, many of them are gases, right? Now, covalent networks. So this is a covalent molecular solid, I should say. This is a covalent network. So sometimes, in rare cases, uh, you have a type of covalent lattice. What does that mean? So look at this. This is a structure of diamond. It's not a really that good of a picture because it's made in 3D. So basically, in the diamond, you have carbon atoms which are all bonded with four other carbon atoms in an endless lattice like this. That makes it for a very, very strong structure. Very, very strong structure. It's stronger even than the ionic bond. So we know diamond is impossible to break, impossible. You can't melt it, you can't boil it, because you need to break all these covalent bonds. And pound for pound, the covalent bond is stronger than ionic bond. So this is much stronger than ionic solids. Also, it's an insulator. What does that mean? This can never conduct electricity because the electrons is just trapped between two carbons in a covalent bond, so they cannot move. Also, this is impossible to dissolve in water, right? You have other types of covalent networks, such as SeO2. SeO2 is basically glass. They're not that hard because SeO2 is made of two types of atoms, which makes it less stable than, let's say, diamond. You have other crystalline structures like this, but remember diamond and SeO2. Also remember this one. This is graphite. Let me show you. I think it's better here. Yeah, a bit better. So graphite is special because it is a giant molecular structure, giant covalent structure, but it's made of layers. So you have these, again, it's made of carbon. So you have carbon atoms bonded into these hexagon like structures. These are actually benzene rings. What does that mean? Each of these C's is sp3 hybridized, which means there is a p orbital on each of these C's, and these p orbitals overlap into a huge pi network. So the electrons can actually move through these layers freely. They're also delocalized in a similar way as in metal. Is just a weaker delocalization because p orbitals is much smaller than d orbitals. So the electrons can move here through the p orbitals. So graphite can actually conduct electricity. However, it's much weaker than diamond because you can see, I mean, this layer would be difficult to break here. But the bonds between the layers are actually just normal intermolecular bonds, so just like London dispersion here. So that's why, I mean, you use graphite pens. It's not very difficult to break them, right? So it doesn't have such high melting and boiling points. It's softer, but it conducts electricity. That's important because it's an exception. And here you've got just a kind of an overview of all the properties as they are often given in the AB questions. Please bear in mind it says here covalent networks do not conduct as a solid, but I mean, you have the graphite exception, right? And also pay attention to this. I put this here for a reason. So it says melting point for ionic is high, but melting point for metallic is low to very high. In all the AP questions, when they ask you about the conductivity of, in the melting points of metals, you say very high. You don't say low. I just put in here to show you that you have some rare metals that actually have really low boiling points. But most of common metals, the vast majority, have very, very high boiling point, much higher than actually ionic. Only diamond, basically, and other similar covalent networks have higher. Now let's look at some examples. Classified following solids: CaBr2, SeO2, nickel, and CO2. Okay, so CaBr2, every time you see something from group 1 and 2 and group 6 and 7, uh, you should check your electronegativity table, and then you will see that the difference here is actually bigger than 1.8. So this is actually ionic. SiO2, I told you that's another example of giant covalent network. So that's what this is. Nickel, again, told you that if you've got only one element and it's transition metal, that's basically a metallic bond. And CO2 would just be a normal molecular covalent. Let's see the next one. Hey. Oh yeah, I like this. So please tell me which is which. Let's see. This one doesn't conduct as a solid, but conducts when dissolved in water. That's only ionic can do that, right? This one doesn't dissolve and conducts as a solid. That's obviously a metal, so it's metallic, right? This is a very low melting point. That tells me this is just a normal covalent molecular compound, right? Yep. And this has a high melting point, does not conduct as a solid, does not dissolve in water. This can only be a giant molecular structure. This can be probably diamond, right? And yes, we are right. Let's go to the next one. Block of sodium cracks when you strike it with a hammer, but copper flattens into a sheet. So copper is a metal. Metals are malleable. They have delocalized electrons overlapping the orbitals. So when you hit them, the layers will move, but they won't break. While in the sodium chloride, if you hit them hard enough and the layers move just a little bit, the Coulomb forces would just break them apart. We discussed all this. Potassium chloride melts at 770. CaO melts at 2572. Why? So if you check the electronegativity table, you will see that we've got here two ionic compounds. However, CaO is made out of Ca2 plus ion and O2 minus ion, right? While KCl is just 1 plus and 1 minus. And they're similar in size, which means CaO has higher effective charge. I mean, Ca2 plus and O2 minus have higher effective charge, which means the ionic bond is much stronger, which means the lattice has much higher energy, which means they're going to have way higher boiling point. And again, it's always the case like this in AP curriculum. Diamond and graphite are both made of carbon. Diamond is extremely hard. Graphite is soft, slippery, and conducts along its sheets. Explain both differences. I mean, we did this like 5 minutes ago, and I don't like these two pictures, so just rewind the video, please. Brass is made by mixing zinc into copper. The two atoms are similar in size. Is a good question. Steel is made by adding carbon to iron. Predict how each change will impact malleability and conductivity. This is really good. So, see, zinc ions replacing copper ions to form brass. This is not much of a change. So, malleability will be reduced. You can even say increase is still going to be a correct assumption, but you need to say slightly. So, when you just switch one atom with another of a similar size, there's going to be a slight change in malleability, but there's not going to be a change in conductivity, obviously, because they're both ions, right? So how is this going to change conductivity? However, in this type of alloy, and again, I think 99% of the time they're just going to give you steel as an example. So that's all you need to remember. So carbon atoms really disrupt this structure and make it unable for the layers to slide over each other. So you have a much reduced malleability. Why is conductivity not reduced? Well, even though carbon is has electrons which are much more bonded with the nucleus than transition metals, you still have a lot of iron in here giving its electrons to this d orbitals and delocalized electrons, so network. So it's still gonna conduct electricity. Here you've got CH4, NH3, and iodine. Rank them from lowest to highest melting point. So this doesn't include any of the solids we mentioned here. This question actually includes knowledge from the previous chapter. I've given it here for a reason, just to reinforce a point. So, and they will all often give you this. So they'll mix up intermolecular forces with properties of solids, right? So you got CH4. CH4 has only London dispersion, right? So it's gonna have a very low melting boiling point. NH3 has hydrogen bond. It's also a dipole, but I mean hydrogen bond is the strongest force. So it's gonna be higher than CH4. But I2, as if you remember last class, I asked you to remember iodine. Iodine is an exception. It has extremely strong London dispersion forces, often like this, stronger than even hydrogen bonding. Why? Because it's very large and it has a lot of electrons. So the cloud is really able to polarize a lot. So please remember iodine and remember that hydrogen bonds overcome dipole-dipole and overcome London dispersion. But for iodine, that's an exception. Hey, review this. Let me know if you need help, and good night.